A huge thanks to Brian for sponsoring this video. Good morning, fellow mathematicians! We make another video. So recently Matt Parker released a video over on his channel about the so-called soap bubble problem. It's a minimizing problem where we have to find out the minimizing work curve, okay, of the soap bubble, which is being traced out by it naturally due to conservation of energy and the like. Okay, all good and fine. But we all know Matt Parker and we all know that there is no rigor involved in his videos. He does things very hand-wavy and most of the time neglects any kind of calculations, which is pretty outrageous, and I know a lot of people, including me, who don't like stuff like this. But never mind, this is not the point of the video. During the video he was presenting an integral, which will be used to minimize the surface of the soap bubble. And he stated that the integral is extremely difficult to solve and neglected solving it in the first place. This is not a problem at all because he's doing more pop culture mathematics than real mathematics over on his channel. But I have to disagree with the fact that this is an extremely hard integral, because it's not. It's just a standard exercise that every physics first year has to do at some point. It's really simple, using just Euler-Lagrange. It's just basic stuff, and this is why I want to solve it with you guys today, giving you an introduction on the topic at first, and then we are going to solve it and see what the curve is going to look like, and I hope you are going to enjoy the video. Now we are going to dive right in. So at first I'm going to draw out the problem once again in a coordinate system. So Matt Parker was standing there and he was basically dragging up a soap bubble, covering him from the sides. Meaning, if we were to draw a coordinate system, the soap bubble would look something like this. So we got our y direction up here, we got an x direction and a z direction in some kind of way. Really doesn't matter how you transform the coordinate system. Now, we don't know what the curve is going to look like exactly, so we are just going to suppose that there is some curve connecting 2 points x0 and x1. Okay, let's just call it x0 and x1. And the soap bubble obviously went around him uniformly in a circle. Okay, it was a circular pattern basically being traced out. So if we were to draw around a tiny little bit of borders, it would look something like this. Okay, these are the borders. And now we want to see how we can find out which curve is going to be traced out, basically, which surface is going to be traced out. And for this we are going to do some simple analysis with differential one forms at first. So let us suppose that we are going to take a look at a solid of revolution. We are going to take a look at one stripe, you could say. Imagine it like a stripe of paper being put into some kind of cylinder around this whole structure in a circular pattern. Meaning we are going to have some kind of area, okay? And this is just going to be a tiny little area piece, basically, okay? Imagine it like a cylinder, and we're going to stack infinitely many, infinitesimally small cylinders up until we have this whole soap bubble covering us. Meaning this right here is just a tiny little area piece, a differential one form. Let's call it dA. Also, what we can do is we can take a look at the x and y coordinates a tiny little bit and how these correspond with a tiny little piece, an infinitesimally small piece of, well, surface length, you could say. So at first, we are going to notice that this right here is just going to be the length in the x direction. It's just going to have a certain x coordinate at this point. And also, if you have the cylinder, take a look at it from this side. This part right here is going to be a very, very small piece of length. We are going to call it ds in this case. This is the very small piece of length that we are going to have. And now we are going to zoom in a tiny little bit more. We are going to zoom in up until our curved line is going to become a pretty straight line. Meaning our small piece is going to look like this. This right here is ds. But it comes with a corresponding very small piece of x coordinate, x length, and a very small piece of y length. This right here is going to be our dy, and this right here is going to be our dx. Well, I mean, if you zoom in enough, it's going to be a straight line. Okay, this is how infinitesimal calculus works. And then if you basically just construct yourself the x and the y coordinates, you are going to get a right triangle out on the other side. And we know what we can do with right triangles. We can use Papa Pythagoras, meaning that ds squared is going to result in dx squared plus dy squared. This right here is working out how it is, because these are differential one forms in just one dimension, and we can basically treat them like fractions, you could say. Okay, but in 2 dimensions this doesn't work out easily anymore. You would need a Jacobian and the like for that. But never mind, this is not the point of the video. Now what we are going to do is we are going to divide through the little x element dx squared on both sides, giving us overall that ds differentiated with respect to x squared is going to result in, okay, dx squared and dx squared is going to cancel out to being just 1, and then plus dy dx squared. Okay, thus far that's good. Now what we are going to do is we are going to take the square root on both sides. Since our ds is a positive length part, okay, it's going to also include the positive third in the problem on the process. And now overall what we are going to do is we are going to integrate both sides with respect to x, leaving us with an expression for the infinitesimally small length part ds integrated. Okay, so if we were to integrate both sides with respect to x, we're going to solve a differential equation. The dx is basically going to cancel out, you can say, leaving us just with the solution to our s in the problem, in the process being equal to the integral of the square root of 1 plus, and dy dx is nothing other than y prime squared, and all of this integrated with respect to x. This right here is our really small length element. Now what about the whole area in and of itself? If we take a look at the area, as mentioned before, we are going to stack up infinitely many small area pieces. These are those little rings, those cylinders. By stacking them up, we are basically going to take the integral of all of these. So to get ourselves the area, we are going to take an integral over all the little area pieces. Now what are those little area pieces? On the one hand, those little area pieces are going to consist of, what are these? They are basically just the surface area of our cylinder that we have. Meaning what we need is we need the height of our cylinder, with the height being our ds. So we have our ds in here in some kind of way. And what we need for the surface area is we need our circumference of our circle. What is our circle? In our case, our circle, or the circumference, is going to consist of 2 pi times r, obviously, where our radius is going to be just the x coordinate. So 2 pi times x. And we know what the integral of ds is. The integral of ds is just this expression that we have up here. Meaning this is going to result in, I'm going to track the 2 pi here. This is going to result in the integral of x times the square root of 1 plus y prime squared integrate with respect to x. And this right here is our so-called Lagrangian. We can make use of the Euler-Lagrange equations here now. This is a minimizing problem. And to minimize surfaces or areas or just lengths in general, we are going to make use of Euler-Lagrange. This is just the Euler-Lagrange formalism that you also use in classical mechanics. And this right here is by coincidence a classical mechanics problem. Meaning this right here is our Lagrangian with respect to x, y and y prime. And if you don't know what the Euler-Lagrange equations are, I'm going to leave some links down there in the description. I derived it on vcubing X's channel a while back with him together, and also I have a bunch of other Lagrange problems here on this channel already. Now, what does the Euler-Lagrange equation actually look like? It's a partial differential equation of the form del, and now we are going to differentiate partially our Lagrangian with respect to y at first. And this right here is going to be equal to the differential in our x coordinate of the partial derivative of our Lagrangian with respect to the derivative in y. And this is what it looks like. And this is the equation that we need to solve in order for us to find out what our y basically is. Our minimizing curve in our problem. Now let us go ahead and get started with the left hand side, because this is the really easy side. Now what is the differential of L with respect to y? Our L looks like this. We don't have a y in here. I mean, we have a y prime, but this is not the same. We don't have any kind of y in here, meaning with respect to y, this Lagrangian is just a constant, and constants in differentiation do vanish, meaning this right here is just 0, identically 0. Now what about the other part? What about the differential in x of the partial derivative with respect to y prime of our Lagrangian? I mean, we are just going to take a look at the inner part at first. Okay, inner part is going to give us, we are going to differentiate what we have here with respect to y prime. I mean, our x in this context is just a constant. Now we are going to differentiate the square root of 1 plus y prime squared. Square root is just to the 1/2 power, meaning we have to make use of the power rule at first and then the chain rule in the process. Power rule tells us that we are going to drag the 1/2, so the exponent to the front, reducing our original exponent by 1, giving us to the negative 1/2 power of our discriminant that we got right here. No, not a discriminant, this is the radicand, I'm very sorry. Meaning we get something 1 over square root of 1 plus y prime squared. Now we need to take the inner derivative. Inner derivative is the derivative of our radicand with respect to y prime. Meaning 1 is going to vanish, y prime squared differentiated with respect to y prime is just going to give us 2y prime. So 2y prime. And 2 and 1/2 are going to cancel out, giving us in the process the derivative with respect to x of, okay, we are going to get x times y prime divided by our square root 1 plus y prime squared. And don't forget, this right here satisfies our Euler-Lagrange equation, meaning all of this is equal to 0. And this right here is very cool, because this should remind all of you of the conservation of energy law, and this is exactly what is going to happen. We are going to conserve our energy, and we are going to minimize the energy in our system, being the soap bubble. And do you know what the coolest thing about this is? If you differentiate something and you're going to get 0 out on the other side, well, obviously the thing you differentiate is a constant, meaning we can actually find out what y is very easily by just setting this expression right here that we differentiate equal to a constant. This is just a result that is going to happen. I derived something like this on the conservation of energy already, so you should also watch the video. Maybe it's on in the description if I didn't forget about it. Now meaning, our constant is equal to x times y prime divided by the square root of 1 plus y prime squared. And well, this is very easy to solve differential equation, no problems there. At first what we're going to do is we're going to square everything to get rid of our square root. Our goal for now is to find out what y prime is isolated, meaning c squared is equal to x squared times y prime squared divided by 1 plus y prime squared. Now we are going to multiply this whole equation by our denominator, leaving us in the process with c squared plus y prime squared c squared is equal to what we got right here. We are going to subtract it on both sides, negative x squared times y prime squared. And all of this is equal to 0. Now you're going to notice that if we want to isolate our y prime, this is going to come in handy to use the distributive laws on y prime squared. By factoring it out, what we are going to get is an expression of the form c squared plus, then we are going to get y prime squared and times c squared minus x squared. And now what we're going to do is we're going to subtract, this is equal to 0, we are going to subtract this part on both sides, giving us basically an equivalent relation here with a negative in the front. If we got a negative here, we can track the negative sign into here, giving us overall c squared being equal to y prime squared times x squared minus c squared. And now we are going to divide both sides by this part, and then we are going to take the square root, the positive square root at that, because our y is a positive function. We are just going to take a look at it from the positive direction, you could say. Meaning overall, our y prime is equal to c squared divided by x squared minus c squared, but the positive square root of this whole thing. Taking the square root is going to get rid of our square up here in the numerator and giving us a square down here in the denominator. And now we can find out what our y is by integrating both sides with respect to x, obviously. It's a differential equation. So let us integrate both sides with respect to x. Now if we do that, obviously, basically our differentials are going to cancel out, giving us y with respect to x. Now y with respect to x is going to be equal to, okay, we get c as a constant here, let's bring it to the front, constant times the integral of dx divided by square root of x squared minus c squared. Okay, this integral is also extremely easy to solve. You should see at a glance that this is going to result in some kind of trigonometric or maybe hyperbolic integral. But we have to go clever about it. Namely, what we're going to do is we're going to factor out c squared down here in the denominator. If we were to factor it out, Dragging it to the front, using the multiplicative property of the square root, is going to give us the square root of c squared, which is just c. So c divided by c is going to cancel out. Okay, this is nice, giving us the integral of dx divided by the square root of, factoring it out, giving us a -1. And now if we were to factor it out, we need to include our c squared somehow on our x squared by dividing by it. And then we are going to just get x squared divided by c squared, or in other words, by using exponent rules, x divided by c and the whole thing squared. And now we are going to introduce a simple substitution. Let x divided by c be equal to, okay, now we need to think about it. You can either use trigonometric or hyperbolic substitutions here. Let us think about the fundamental Pythagorean theorems that we got. So on the one hand we got cosine squared plus sine squared being equal to 1. Okay, this is something that we could possibly use here. On the other hand, we also got the hyperbolic counterpart, namely that cos squared minus sinh squared is equal to 1. Now, what we are going to do is we are going to solve this equation right here in a way such that we get something squared minus 1. What we are going to do is we are going to add sinh on both sides, and then we are going to subtract 1 on both sides, giving us that the sinh squared is nothing other than the cos squared minus 1. So it does make sense in the context of hyperbolic functions. You can use others. There's no limit to it actually. In the context of hyperbolic functions, it does make sense to substitute the cos for our x divided by c. So let's say this right here is equal to the cos of t. Differentiating both sides, giving us, okay, differentiating this with respect to x is going to give us dx divided by c. Let's bring the c to the other side. So dx is equal to c times the differential of cos of t with respect to t. Differentiating the hyperbolic cosine is going to give us the hyperbolic sine in the process. So sinh of t with the differential 1 form dt. Now we can plug the new information in, giving us overall that our y with respect to x is nothing other than, okay, we are going to get a c as a constant, which we are going to just bring to the front. C times the integral of. Now we are going to get sinh of t dt divided by, and now we are going to get the square root of cos squared minus 1. Cos squared of t obviously, but I'm going to leave that out for now. This really doesn't matter. Now, what we just found out is that cos squared is nothing other than cos squared minus 1 is nothing other than sinh squared. I'm terribly sorry. So meaning this expression right here is the square root of sinh squared. But the square root of a square is just going to give us the argument in itself, sinh. Meaning sinh and the square root part right here is going to cancel out, giving us just c times the integral of dt. And integrating dt is really easy. This is just c times t, or we know what t is. Namely, t is nothing other, if we were to use inverse hyperbolic cosine here under the condition that it's bijective on our interval, we are going to get that the inverse hyperbolic cosine, also known as area hyperbolic cosine of x divided by c, is our t. Meaning the solution to our problem, y with respect to x, is equal to c times the hyperbolic cosine, but the inverse 1 of x divided by c, plus some arbitrary constant, let's call it kappa, really doesn't matter. And this right here is the solution to our problem. Now you might ask yourself, hey, Matt had a different expression. He just had cos in his expression over on his video. Well, for this what you have to do is you have to solve this equation obviously for x by subtracting kappa on both sides, then dividing by c. And after that you are just going to take the cos on both sides and then multiply everything by c once again. He did get this expression because his coordinate system was shifted. But if you use a shifted coordinate system, it's going to be so fucking complicated. You don't want to do this, trust me. So in order for you to get the same cos, the same cos function that he did before, you just have to do a reflection basically in our origin, turning this around, giving you x with respect to y, basically, as a function. But this doesn't matter at this point, because this right here is our final answer, and feel free to solve everything for x. And this concludes what I had to say. And if you did like what you have seen today, if you're interested in more classical mechanics, Lagrange mechanics, minimizing problems, and all of the like, then I invite you to check out the contents of today's sponsor, Brilliant, who were kind enough to sponsor yet another video here on this channel. Now, that one was a lot of fun for me. It's just I haven't done really higher mathematics or physics here on this channel in quite a while. I'm not into that anymore too much at the moment because I'm teaching at a school. But I love to go back to these fundamentals to just brush up on my old knowledge once again. And if you feel like you forgot something from your university, from the times you studied at school, etc., then maybe Brilliant could be the perfect source to brush up on some old topics that you forgot about. If you're not familiar with Brilliant yet, it's an online learning platform and app with nearly 70 interactive courses in all topics STEM. Classical mechanics, Lagrange mechanics, mathematics, all of this is basically just applied mathematics, you could say, and the like. No matter what you're looking for, chemistry, etc., they definitely got something up their sleeve for you. And all of this will be packed into nice little interactive exercises, which are going to help you learn a new topic step by step, but really in depth. And you are going to go out of their courses way smarter than the way you went in. It's just absolutely crazy how well they basically transfer the knowledge to people. And the interactive learning concept is just really spicy. I can't put it better into words. Just if you take a look at their analysis sections, calculus sections, physics sections, if you were to have a graph like this, they would allow you to drag around levers and the like, just varying the parameters overall, seeing how the curve is going to transform under coordinate system or coordinate transformations in general. And this interactive learning concept is really unique. I haven't seen it anywhere else before, and this is just why I love Brilliant so much. They really know how they can make you understand the topic. And this is something that I find rarely on the internet. And this is why I'm recommending Brilliant to you, because it's how I learn new stuff from time to time, and I think you should learn new stuff that way too. And if you feel like this is something for you, if you wish to try it out for yourself, then definitely make sure to check out the link at the top of the description, brilliant.org/FremdelMaths. With it, good news, you're going to get free access to a big portion of Brilliant already, but more importantly, the first 20 people to actually make use of the link get 20% off an annual premium subscription, which is a freaking great deal considering how much courses and content they have available on their website already. So definitely make sure to check it out and support the channel this way. Otherwise, if you did enjoy this video, then definitely make sure to subscribe to the channel, and also don't forget to subscribe to Flammy's Wood, my woodworking channel. I still have a lot of wood lying around. That's a big old board of mahogany. What a fine wood. Yeah, I want to show you guys this. This is a new cutting board I created and it looks freaking beautiful. You can also get it over on stemage.eu if you're interested. Yeah, I just like it so much. It looks so good. And other than that, don't forget to stay safe, and I'm going to see you soon on the Advent Calendar 2021. Have a good one and please stay safe. Ciao.